Good evening. Welcome to the U.S. Geological Survey and another in our continuing series of evening public lectures. My name is Leslie Gordon, and it's always my honor and pleasure to introduce our speakers. Before I introduce tonight's speaker, I want to make sure you all come back next month. There are flyers, I think they may have disappeared, but I'll find some. Next month, geologist emeritus, or actually a seismologist emeritus, Ross Stein, will be speaking about the gold rush and the 1906 earthquake, how they combined to create the breakthrough discovery of modern seismic science. So please do join us next month for some insight into the study and the history of the study of earthquakes. Tonight, it's my pleasure to introduce Jonathan Stock. Jonathan's been here in Menlo Park with the U.S. Geological Survey since 2003. He started his career here as a postdoctoral fellow with the Mendenhall program. He is also, in addition to being a research geologist, Jonathan is also the director of the USGS Innovation Center for Earth Sciences. It's kind of a fun, innovative partnership among many companies and organizations and agencies in the Silicon Valley area. In his, when he's not being the director of that, Jonathan uses mapping, real-time monitoring, and modeling to understand the effects of climate and land use change on the hazards and evolution of steep landscapes. He's currently working on some real-time monitoring of shallow landslides and debris flows here in the San Francisco Bay Area and Northern California. He is forecasting, or attempting to, what's the right word? Forecasting geologic hazards from future storms, the effect of land use on maintaining Department of Defense training areas, and coral reef pollution in the Pacific, and the evolution of hazards and alluvial fans. John Stock holds degrees from the University of California, Santa Cruz, the University of Washington, and the University of California, Berkeley. Tonight, John's going to talk about the last lands, how humans changed erosion in Hawaii. Please welcome John Stock.
Thank you very much. Thank you very much, Leslie. How's my sound? Can everybody hear me in the back? Good. Thank you, folks. Thank you for showing up. Thanks to folks online for showing up. You are looking at an image of the island of Molokai. Now, let's see if I can get this to work. There we go. The steep north face, this escarpment, is arguably the headscarp of an ancient landslide that collapsed half the island into the sea. As the trade winds come in from the northeast, they rise up and then precipitate water out over the wet side of the island here. By the time they come down on the leeward side, it's relatively dry. When the first Hawaiians arrived here, about 1,000 to 1,200 AD, this is probably about what they saw. This is one of the rare photos of Hawaii where you don't see the big towering, infrastructure of Honolulu gleaming out. This is probably pretty close to what the first people arrived. This was the last habitable place on Earth that humans colonized. 60,000 years ago, roughly, Homo sapiens came out of Africa. It wasn't until about 1,000 AD, roughly 1,000 years ago, that they found this last place. And so the story I want to tell to you tonight is one person's view, my view, of how humans have changed erosion in roughly the last 1,000 years in Hawaii. Perhaps the significance is that this is the place where the print of humans, the thumbprint of humans on the landscape, is the most recent, and therefore it's a place where we can eke out some of the answers to what the ancestral thumbprint, think of that, 60,000 years of human imprint on the rest of the world, might be. It's a story that's based on about 10 years of fieldwork and monitoring. It is a team effort. I'm going to present it to you, but I will tell you that people like Mike Fields in our Coastal and Marine Group, Gordon Tribble, now in our Pacific Islands Ecological Research Group, and many other USGS folks that I'll point out as we go along, have played fundamental roles in the understanding here and making this research possible. But I will also say that what you're going to see tonight is my view of the problem, and that there are other views, but I'm going to tell you my view is pretty good. So let's go ahead and we'll take a look at that. So in the beginning were the rocks, and the image that you see here shows you the rocks. On the lower right-hand side is the big island of Hawaii. Those of you who fly into Kona fly in just about here on that red recent flow. The red are very recent volcanic flows, and the ages on this island are 0.7 mega annum, or million years and younger. And then you will all be familiar with the notion that the Hawaiian Islands, the rocks get older as you go west, to the point where when you're over on Kauai, you're about 4.15 mega annum, or million years, and in between, the ages are in between. They do this, we think, because this piece of crust is drifting over a fixed hotspot, and that hotspot generates a plume, a tower, that hits the crust, melts, and generates the islands. And this process of island generation has gone on for many tens of millions of years, and you can trace the ancestors to the Hawaiian Islands many hundreds, and in fact thousands of kilometers out to the west. But today I want to talk to you about 3 places in the islands. We'll start here on Molokai, we'll move to West Maui, and then we'll come to the Big Island. And I want to tell you a story about my view of how humans have changed things there. Here's a picture of Mauna Kea. Mauna Kea is just under 14,000 feet high. The image that you can see the telescopes up on the top here. Of course, it's one of the clearest places in the world to image the heavens because you're in the middle of the Pacific Ocean. There's hardly any more remote places than this. You see a rumpled surface here, which are lava flows, ancestral lava flows. And then you see little cinder cones popping out here, places where vents have erupted and put fragmental material on either side. One of the big products of volcanoes is lava flows. This is an image of the kinds of lava that come out of that volcano and others. You can also see the classic VOG here above Kailua Kona. If you were to take a cross-section through this flow, you would see a solid sort of flow interior where the lava has cooled. You would see what geologists call the autobreccia layer. That's the sort of pie crust like cooled outer skin of the lava that the flow then rolls over and leaves behind as a rubbly breccia. And then importantly, underneath it, you see this red material, which is essentially fine sand and silt. That is an airfall. By airfall, I mean that is a piece of the magma that has been blown out of a vent, turned into a very fine particle like a sand or a silt, and has drifted on the air and then fallen on the landscape. We do not typically think of Hawaii as a place where we see a lot of airfall. And if you look in textbooks, they will tell you that Hawaiian eruptions are not explosive and we shouldn't expect airfall. But in fact, what you will see tonight is there's an awful lot of airfall there, despite what the textbooks say. So maybe I've got it wrong, but on the other hand, I got a lot of observations. So this turns out to be pretty important into the story of erosion, because this is the material that turns Hawaiian waters from blue to brown. And so we'll follow that story. Here's another image of the same feature. This is a lava flow. This whole slope here is essentially about a 20,000-year-old lava flow. This is the edge of it, that autobreccia layer. And then notice this white material underneath. That's the fine sand and silt. That's the airfall. That fell out of the sky. And it's essentially a sand pile sitting there waiting to move. You can see the same sort of features. This is a cross-section now of part of Molokai. All of these thin lines here are lava flows, typically about 3 feet thick-ish. And then notice that as you get towards the top, there are these red layers. That's the same material you just saw. It mantles the upper parts of this topography in the flat areas. And so on top of that stack of lava, and sometimes in between it, there are these airfall layers of fine silt and sand. And they matter. I'll show you why. What do they look like? This is a plot that shows you the grain size, and it shows you this is 100% clay on that axis, 100% sand over here, and 100% silt. And these are many samples of airfall that I've taken from the field areas you'll see today. And what you see is that a large number of them live closer to the sand end member. They have low clay contents, and some of them get kind of silty. And this is sort of the general range of particles that we see. That means that these things can float in the air for long distances, and it also means that water can move them easily. Before people got to Hawaii, all of those fine-grained deposits were locked away under vegetation. You're looking at an image of one of the last sort of remote, wild parts of Hawaii. This is Pelekunu Valley on the north side of Molokai. Today Mel Beeson, who's a geologist of ours, was telling me the only way he took a helicopter in here, and the only other way to get in is by boat. There's almost nobody living there. and it represents probably what the landscape looked like before people got there. A dense mass of vegetation covering pretty much everything. In that kind of landscape, erosion happens episodically as trees are blown over by wind and the soil in the roots moves downslope. During very large storms, pore water accumulates in convergent parts of that steep landscape, and you can essentially liquefy a part of the hill slope, and it slides down as a landslide, mobilizes a debris flow. And then you can also get, very commonly, this mass here on the north side of Molokai is a rock avalanche, a section of the cliff that essentially fell away and collapsed. All of these deposits share one thing in common. They don't have a lot of fine-grained material. They are largely boulders, and if you try to landscape your yard with them, you get a bouldery yard. If you go down to the landscape in Hawaii where all these things collect, the river valley bottoms, what you see in places where there hasn't been much human interference is a lot of boulders sitting around and some fairly clear water and very occasionally some sand and bedrock. You do not see a lot of silt or clay, and you see a low amount of sand, right? When you, if you're there during large runoff events, you can look at the water, and it often coming out of this sort of undisturbed parts of Hawaii will have this tea color, which represents, we believe, organic materials as opposed to sediment. The waters have very little sediment in them. So consequently, the picture I'm painting to you, and I can show you some graphs later on if you like, is that the erosion rates before people influence this landscape are remarkably low, much lower than we have here in the Santa Cruz Mountains. And those rates represent the slow episodic movement of silt, sand, and sometimes big rocks down to the near shore. I mentioned before, Hawaii is one of the last habitable places that people got to. Here's an image that Pat Kirch, one of the deans of Pacific Archaeology and a colleague, has made. And what you see here is a map of the Pacific. Let's see if I can get the mouse to cooperate. And this red line represents Pat's archaeological evidence for where people got to 40,000 years or earlier. This is essentially the malarial belts. Anybody in this neck of the woods, their population was pushed down by malaria. The outer islands, which you see, all these nice places that we can fly to and sit on the beach now, were uncolonized by humans prior to about 1500 BC. And then something extraordinary happened. We think in Taiwan, a group of people who are the ancestors of the Polynesians developed the technology to navigate across vast swaths of ocean. And those people literally exploded out of Taiwan and colonized much of the remote Pacific in that space of 1500 years BC to roughly 1000 or so AD. But what that means is that all of this broad terrain from Johnston all the way down to Rapa Nui, all of these lands were the last places on Earth settled by people. And the imprint of these people is recent. And of course, Hawaii sits way out at the edge of this at about 1000 to 1200 AD conservatively. You can see older ages, but there's debate about those older ages. It's a pretty safe age. So remote Oceania, as Pat says, free of human influence until about 1500 BC. And of course, once you get out of the malarial belts, your ability to grow your population dramatically increases, and that has big consequences for the archaeology. So here you're looking at some excavations I was involved in with Pat. This is a little hearth up here. This is a map of a place on the south side of Maui called Kahiki Nui, where Pat and his colleagues have spent a lot of time documenting archaeology. It's not a very, very friendly place. This is not your average picture of Hawaii. You've got crashing surf. It's pretty damn dry. You wouldn't want to make a living here, and yet, look at all the structures here. Most of these structures are about 1500 to 1860. So what happened is, as that population exploded, it's kind of like Silicon Valley here, every available piece of land got eaten up that could be eaten up, and people got pushed further and further out into less habitable places. And so in essence, part of the story of the human colonization of Hawaii is the competition for resources, and the consequences of that, as you'll see, are that they change the landscape. I'll come back to this theme when we hit fire. Okay? Fast forward to current, right? There's also competition here, right? Try and buy one of those condos. It doesn't come cheap. You're looking at an image, of course, of Waikiki in Honolulu on the island of Oahu. This is the reason most of us go to Hawaii. And the graph down below shows you what it means for Hawaii. This is a graph of months from January 2002 to, I can't quite read that, I think that's 15. Okay, thanks guys. And this is visitor expenditure in millions of dollars per month. And so what you see, the average of this line, this is $1 billion. In essence, the Hawaiian Islands take in $1 billion a month. That's their tourist industry. It's above that right now. And why do they go there? Why is that $1 billion spent there? It's blue water. It's blue water and all the power that comes from that blue water. And of course, the Department of Defense plays a role in that too. But $1 billion a month is pretty decent change. You do not go to Hawaii to swim in this. This is West Maui. I do not like to swim in orange water. I don't know about you. Most people don't either. And so if all of Hawaii's waters turned orange like this, that $1 billion would evaporate. Or at least it'd be a very small fraction of it. And in fact, I've been to places that are exactly like Hawaii, except for the fact their coastal waters are polluted. The Comoro Islands, just off the coast of East Africa, are a direct analog for Hawaii. But if you go swimming in the Comoros, it's orange water, and you come back with someone else's clothes because they throw all their trash in the water. Right? So Hawaii is this powerhouse because of its clean blue water. And yet, in the last 10 to 20 years, more and more folks are looking at the arrival of these kinds of waters. Here's West Hawaii. This is Pelikane Bay, and if you look south, the CEO for Salesforce has this mega compound somewhere in this image. And what you see again is brown water coming in, and then very faintly out there on the horizon, you can see the boundary with blue water, right? So brown water means not very good swimming. It means that the coral reefs that create the ecology for that place are threatened. And it means that the whole sort of culture of Hawaii that's based on extraction of resources from the near shore is threatened. So everybody wants to know, where's it coming from? Is this amount normal? By which they mean this can't be normal. And what can we do about it? This is an image now of Molokai. And I'm going to spend the first part of the talk on Molokai because it's the place where we've invested the most resources to figure out the answer to these questions. I'm going to talk about animals. Very cute goat. Turns out goats are part of the problem on Molokai. Goats make blue water into brown water. So goats are part of the problem. There's a rich and long history of cattle in Hawaii that probably have contributed to it. But essentially, what both Hawaiians but mostly post-European colonists have brought are animals. And where those animals have sort of gotten out of control, they've created issues. Okay? The second theme I'll hit, this will be on West Maui, is agriculture. You see that red soil in the front? That's that old airfall. Those are silts and sands that all you've got to do is rain on them a bit and off they go. Agriculture redistributes where they are, and that redistribution matters. Most of you will be familiar with the sugarcane industry and the pineapple industry. It used to be a lot larger in Hawaii. In fact, it used to dominate the islands. The legacy of that is one of the things we'll explore. And the third theme I want to hit is fire. This is an image from Molokai. You see a couple of twisters there. This was a burn in 2009. Burning fundamentally changes the landscape. It changes how water interacts with the landscape, and it changes how sediment moves. And so we'll talk about the arrival of fire with the native Hawaiians and how that changed the landscape. Back to Molokai. There are many ways to approach the problem. One of the ways that the survey, I think, has a unique legacy is mapping, monitoring, and modeling, or what I call M3. Since 1879, our folks have gotten their boots dirty on the ground and gone out and mapped things. So if you want to know where sediment is coming from, there's nothing like going out and actually mapping it, and you can do that. If you want to know whether the amount is normal, there's nothing like taking those map units and installing monitors there so you can estimate the rates at which sediment is moving. And then ultimately, you want to take those two things together and make models that create a compelling political case for economically viable mitigation. In other words, where can I most reduce the amount of brown water coming in without spending all my money on one thing? So the theme that you'll see me pursue is this M3 theme. We'll start off by mapping the landscape to tell you where the sediment comes from. You'll then see me talk about a bunch of pointy-headed instruments we put out to tell us how fast it's coming, and then we'll try and integrate those together in a very crude model. So here's Molokai. This is an image of the island, hill-shaded DEM. The bright-colored patch over here is the watershed that we'll focus on. It's called Kawela, which means in Hawaiian, the heat. It is the dry side of the island, and it is hot. It's about 13 square kilometers, 400 millimeters of rain down in the base here, 1,200 per year. This is millimeters per annum or per year at the top. It's wet up here. It's really dry down here. There's a USGS stream gauge down here that tells us how much water and sediment are coming out of the whole catchment. And then I'm going to show you an experimental hill slope here where we monitor the same things, and then we've got a distributed set of observations and measurements throughout. The image you're looking at now represents, in essence, what has happened to Molokai since the arrival of this cute little critter here. He's essentially, or she, has turned this landscape here into this. So the red color here is, again, that airfall. It's sand and silt that falls out of the sky, mantles the topography, and then sits there under vegetation until the vegetation is stripped. Once the vegetation's gone, the stuff is accessible every time it rains hard enough to pond water and move it. And so the reason that this is green and this is red is there's a fence here, and these little critters don't get up here. So goats in Molokai have turned blue waters into brown. Here's an image that gives you another sense, another way of looking at that same problem. You see a slope here that curves. See that lovely curve? It's sort of, the slope gets larger and larger as you go down slope. There's a mathematical expression here. It describes why the slope gets larger, in essence, because by the time you're down here, you're moving all the sediment that's above you in addition to the sediment that you have here. So as the slope steepens, you could move more sediment, and you've got more sediment to move. This is the signature of that slow, episodic creep of sediment down the slope by trees falling over and by animals as well. There's another signature here. It's eating into it. This is a concave up signature. This is the signature of flowing water. So this is water that's generated when it rains hard. It erodes, and it creates essentially a river, a concave up river. So this conversion is a change from geomorphic processes that are slow, low magnitude, low erosion rates, low lowering rates, into much more rapid erosion rates as you remove the vegetation, and water can now access those fine sediments. We have other evidence that this has happened pretty recently. So here's an image. You're looking, this is a cliff up here. This is a view of it from on top. And cliffs generate lots of coarse material. As those rocks fall down, they create a talus pile, which is largely coarse boulders from rockfall. And that's what we expect to see here. But notice what's on top of it. On top is a wedge of red material. It's our airfall again. That airfall has been generated by a change in the material that's coming off that landscape. As the goats have gotten in here, they've opened a window into that fine sediment, the airfall, and now it's being deposited down here by overland flow. So how do we map these processes? What you're looking at is now a map of the watershed. The watershed is in yellow. The different colors here represent different processes moving the sediment. Let me walk through a few of those processes. In green is the way things used to be. This is where the vegetation still persists. It's beyond the reach of the goats. You have trees, you have bushes, and the fine sediment is locked away beneath them, and it moves when they move, when the tree topples over. Slow, low magnitude. In pink are cliffs. This is essentially rockfall. Not a lot of fine sediment coming from rockfall. That's mostly boulders. So 2/3 of the catchment area immediately is not a good source for the fine sediment that's polluting this nearshore reef out here. This gold color here, which is essentially the same as this color here, these represent places where those airfall deposits are thin and discontinuous. They're there in little patches because they've mostly been eroded. And then you'll see a few other small patches here. See those guys there and there? These are places where the airfall remains as a deep pocket of fine silt. And in those places, as you will see, the erosion rates are actually much higher. So it turns out, to short the story, that a lot of the erosion that's polluting the nearshore here is coming from these little pockets, which represent about 2% of the total area, because that's where all the fine sediment is. There's some other things here. The yellows here are alluvial fans. That's where the sediment gets deposited on, in some cases, before it goes out to the nearshore. In other cases, it bypasses the nearshore. The red here are debris flow deposits. These are big rocky flows that are different from river flows. And there's a few other things on here. But by and large, the message here is that 2/3 of this watershed doesn't produce fine sediment. of the remaining 1/3, there are local hotspots that produce potentially a lot of it. So now the next thing we're going to do is go look at one of those hotspots. So here's an image. It doesn't strike you necessarily as a place with a lot of fine sediment, but if you look carefully in between the rocks, you see all this red. This is that airfall again. It's covered by a thin veneer of cobbles here, but in fact, this is a many meters deep old deposit of volcanic ash that's fallen on the landscape and been preserved and is now being re-excavated as the goats have stripped the vegetation away. So all the instruments that you see here are an effort to estimate how much water and sediment comes off this. So here's a little flume. We call it a partial flume. The flume is connected by a pipe to a pump sampler here, so we can essentially pump out samples of the water-charged sediment. And so by doing this, we can estimate how much water and sediment come out of this 2,000 square meter catchment. This is a rain gauge. This tells us how much water goes in. And then we have overland flow meters. These essentially tell us the depth of the flow across the surface when it rains hard, that unconfined flow. I'll show you some pictures of that in a second. We have some soil moisture loggers, which tell us what soil moisture is. And then there are about 60 erosion pins, and these are essentially nails that we put in the ground, very crude, and nonetheless really effective. It turns out that they pretty much match the answers we get from more evolved techniques. We simply measure how much the nail sticks out each time we come back and then reflush it. Not bad, particularly when it gives you the answer that tens of thousands of dollars of other techniques give you. You might not believe it without those, but boy, you believe it with those. So here's, if you turned around at that site and looked out towards the sea, you'd have another glimpse. So this is the ridge to reef concept. We're sitting up here on the ridge. This is the source of sediment, this thick packet of fine sediment. When it rains hard, this stuff basically moves all the way down this valley and out to the reef, and it can do it in a matter of hours. So the next image is going to show you what it would look like to stand there during a rainy day. So here what you see is the same place, but now you see water ponding in these depressions, these little storage areas in the soil. Once it fills up those sinks, it overflows into the channel head. And now notice the brown muddy color, a lot like what we saw out on the reef. This water is on a fast path all the way out to the reef, and there's turning your blue water to brown water. Here's another view of the same thing. This is what I mean by overland flow. You can see a thin, discontinuous and different thickness layer of water. It's essentially picking up the fine airfall here, moving it downslope and out to the sea. So that's the mechanism of erosion. Now, let me take a brief moment to describe a graph that shows you that event that you just saw. On the x-axis is time, so this is 2007 moving forward over the course of about a half hour or so, a little bit more than that. And then there's a couple different axes. Let's start with rainfall. So this is rainfall intensity in millimeters per hour. Let's say an inch, or let's say a half inch would be about 12 millimeters an hour, right? So there's about a half inch. So so notice the rainfall is this line here. This is the average rainfall. So let's look at this. It rises and then plateaus and then comes back down again over the course of, roughly close to 45 minutes, right? The blue line here represents the runoff. That's the discharge. You can see that's over on this axis. And so notice that when it starts raining close to a half inch an hour, or about 10 mils an hour in this case, that's when we start to generate runoff. Before then, the water is seeping into the ground and is not eroding. As soon as it starts raining harder than that, it's flowing over the ground and moving sediment. Okay, so the first thing we learn from this is, hey, guess what? Now we know when erosion happens here. It's when it rains harder than 10 mils an hour, or crudely half an inch, which interestingly is about the threshold for Bay Area widespread landsliding here. That's another story. On the bottom is a bunch of sediment collects. Remember I said the ISCO pump sampler grabs that water out? Well, here it is. We start off at 2220, let's see, where are you? 2252, where are you? Oops, I'm off the scale. 2353, there I am. So there I go on, I start grabbing sediment. And then notice that by the time I get to about 3 minutes past midnight, I've got my sediment peak, and then after that it declines very rapidly. But notice something interesting. In fact, the water is still, and the rain are still going along pretty steady, and yet we're losing sediment. So this tells us something rather interesting. It tells us that we're in what geomorphologists call a sediment supply limited environment, which is a fancy term for what happens when you sweep your garage out the first time and get a bunch of stuff out, and then you go back the second time and you don't get very much out at all. your cement garage floor is a sediment-limited environment. It'll produce that first batch, but once you sweep it out, with rainfall this time in your garage with your broom, hopefully, once you sweep it out, there's not a lot left. That sediment isn't going to produce a lot. Sorry, that cement isn't producing a lot of sediment. So this terrain behaves curiously in a very similar way. The first rains that come in the fall do most of the sweeping. After that, you don't get as much out. Here's an image of what that looks like. On the left, you see a water smooth surface. This is that airfall, but now it's had its loose, crumbly stuff removed and it's fairly smooth. But on the right, you see just beyond the reach of the waters, that thick weathered layer, like a skin, if you like an exfoliating skin. It's around a centimeter to a centimeter thick. And that's generated every season. You generate this weathering layer, right? And then the rains come and sweep it away, and then it gets regenerated. And curiously enough, there's not much of a spatial pattern. So essentially, you get the same lowering rate all across the exposed airfall in this place. What's the relationship between rain and erosion rate, right? You could ask, it's great, we can't monitor all the time. Can you give us a simple estimate? Here's a graph which shows you the lowering rate, which is simply the erosion rate, if you like. This is how many millimeters the surface lowers or erodes. Versus hours above 35 millimeters per hour rainfall. So this is a pretty intense rain. And what we find is, based on the past decade of monitoring, that essentially there's a pretty linear relationship. And if you take the number of hours above 35 millimeters per hour, multiply it by around 4 and some odd, add 2, boom, you get about the answer. Is there any physical significance to that? Well, not the exact numbers. This is not a mechanistic model. But what it does tell you is that anytime you're raining above you remember we talked about that 10 millimeters per hour? Once you rain above 10 millimeters, now the water isn't soaking into the ground. Now it's running out over the ground. And so in essence, if you graph the amount of time it spends above 10 millimeters per hour, I've chosen 35 here. You can choose 20, you can choose 40. They give you different linear relationships, but they all give you a decent relationship. They all tell you that the amount of time that landscape spends with water running over it varies linearly with the erosion rate, right? Now, it turns out 35 happens to work better than the others because it's a nice compromise. The harder you rain, the bigger the raindrops get. And the bigger the raindrop is, the more impact it has when it hits the ground. And so 35 turns out to be, a common rainfall. Once you get up into 40 and 50, those aren't as common. But 35 happens frequently, and it's also the most energetic rainfall that happens frequently. So you can go through a frequency magnitude argument and get there. But in essence, any value above 10 millimeters per hour in this case, which is the rate at which it begins to pond on the surface, will do the job for you. So that's a nice relationship. Does it work everywhere? Probably not. But it probably works for a number of areas around Hawaii, and we're in the process of trying to show that. So if you make a brief point here, notice these are lowering rates per year. So that's 14 millimeters per year. That's something like this. That's how thick that skin is. Now earlier we asked the question, is this amount normal? And that's why we're doing all this work, is to give people a sense of, is this normal? Should it be like this? So here's a typical Hawaiian range of incision rates. This is a graph that shows observation time, how long you measured erosion over, versus lowering rate or erosion rate, going from 0.01 millimeters per year, which is pretty small, up to about 10. So we're measuring, in the place we just looked at, we're measuring about 10 millimeters per year. And what we know from other sources of evidence is that typical Hawaiian rates should be closer to 0.1. So one of the things that comes out of this study, and there's a lot of other data I could show you, is that essentially what goats have done by removing that vegetation is increase the lowering rate, the erosion rate of that landscape by 100 times. So what used to be a slow episodic trickle of sediment down to the reef is now a flood of sediment every time it rains harder than about 10 mils an hour. So if we take those numbers and we add some other numbers to them. So in addition to this hotspot that we've instrumented, we also put erosion sites all up and down the access road here. And in those sites, essentially we get about 2 millimeters per year of lowering from rocky soils. So these are soils that are the remnants of airfall, but they're sort of patchy and there's not a lot of soil left. We also get deposition rates down here in the fan. So some amount of that sediment is actually still being deposited on the fan. And then we've got a long-term incision rate that generates fine sediment from, a small amount of fine sediment from soil creep and from rockfall that's around 1/10 of a millimeter. It's probably lower, but that's pretty close. So what we can do is make what's called a sediment budget. A sediment budget is a table that shows you how much sediment comes from each one of those mapping units. And so in this case, it turns out that these little hot spots where we spend a lot of our time, these thick pockets of old airfall, represent 2% of the area, but about 4,600 tons, so almost half of the total sediment that's coming off this landscape via this estimate. Then we get about 7,800 tons from the rest of this big drainage area that's, this color stuff, overland flow, and then a much smaller number from rockfall and soil creep areas where we're not producing a lot of fine sediment. And overall, we get around 12,000 tons per year, so this model suggests. And then here's what's actually coming off there. The stream sediment gauge down here that the USGS runs actually measures, gives us an estimate of what's coming out of the whole catchment, and it's about 6,000 tons, or half of this. So we're not bad, we're actually pretty close considering. Now we can improve on this a bit, and it's very tempting to do that by putting something else in. So the colors that you see here are vegetation. These are different kinds of vegetation, and this is vegetation that's locking fine sediment away. So in the first map, we assumed we ignored vegetation except for this big boundary here between canopy and shrubs and grassland. But it turns out out on the shrubland, out on the grassland, I should say, there actually are patches of vegetation. And so if you take those into account, then in essence what you do is reduce the amount of area that's open to erosion, and you get about 2,600 tons, 1% of the area, 3,600 tons down from that bigger, and 100 tons still, because we haven't changed much in rockfall country. And we get fortuitously close. Now these numbers are, you'd never get that twice, and I wouldn't put much value in the fact that this is that close. But what I do put value in is the fact that we've taken a number that was too high, and by appropriately shielding it with vegetation, pushed it closer to the actual number. So I guarantee you, if I do this next year with different numbers, it'll be like 8,000 or 2,000 or 3,000. It'll be different from what the real one is, but it's pretty darn close. And that of course is the point, is we're trying to come up with models that we can apply elsewhere. So one of the lessons that comes out of this mapping, monitoring, and modeling here in Molokai is that we can essentially, by mapping the terrain, by including vegetation in it, and by monitoring, we can come pretty close to what the gauge actually tells us. And whether it's 12,000, which is not bad, or 6,000, we'd be happy to have either one. So that's pretty good. And then something happens. So the story I just told you is the story of what happens when there's lots of goats around. But after we told this story to Nature Conservancy and to other folks who already knew it kind of, but they just didn't know the numbers, essentially what we gave them is the ammunition, pardon the phrasing, that they needed to tell the hunting community and the other folks in the island, look, we've got to take care of our goats. We've got to knock down our goat population because they're turning blue water on the reef into brown water. And so as a consequence, a lot of folks on the island suddenly woke up and said, let's go get some goats. And in fact, that's what you see these two gentlemen doing here. They're pretty good shots. Those are 30-06s, and the guy on the left is home from Afghanistan to do some other kind of shooting, I guess. So these guys are actually friends. And as a consequence of efforts like this, as well as, more importantly, actually aerial hunts, here's an image. This is Jim Jacoby's work now, one of my colleagues. This is what the landscape looked like in 2009 when the goats were at full bloom. Maybe 1% you could find tiny scared vegetation hiding in between boulders. But after the goats went away, mostly, we started getting vegetation back. And by the time 2013 had happened, we had vegetation cover that had gone from 1% up to 20 to 30. So over a very short time scale, that area turned from bare, exposed airfall into vegetation. And as a consequence, something pretty exciting happened. This is a graph of dates surveyed. So this is 2007 through 2014. And notice the goats start getting shot around here. And this is the annual lowering rate. This is again, is erosion rate. And early on, you can see the red dots. These are for 2 monitoring sites. The red dots are sitting up here. And we're essentially a centimeter a year. And then sometime in 2010, right around here, the goats start getting knocked out. And look at it plummet. Now we're down a full order of magnitude over the short course of several years. And the same thing for this other one. So Yeah, it's a 3-year period. That's pretty darn short, right? And again, it's because the vegetation came back. So over a very short time period, because you get rid of the goats, you could substantially reduce the erosion. And what we're essentially giving to Nature Conservancy and the community on the island is, here's the data that support the actions you're taking. So again, we're an arsenal. We create scientific data. I'll take a question. Go ahead.
What's the yellow triangle?
The yellow triangle are incision rates from a gully nearby. So they show an even more dramatic change from 20 millimeters all the way down to like 0.10. Sorry, that's not on the graph, but essentially it's a gully that was influenced by overland flow. Okay, so I'm gonna leave that story. This is the story of how goats influenced it, but also how getting rid of goats brings the landscape back, brings it back in the sense that the lowering rate's reduced. And I want to talk to you about another story, and this is the story of agriculture. So those of you who've been to West Maui know that it's a lovely place, Lahaina, the old whaling port, and it's just a lot of amenities. It's got great weather, and of course up in the hills are these old pineapple and sugarcane fields, which you can see here. This is that red airfall again, and a nice rainbow. If you looked at an air photo from 1955, which you are looking at, you would see that much of West Maui is developed for agriculture. Sugarcane, pineapple, those two things dominate. Most of these places are on what we call flow slopes. That's the original flow surface that's been covered by airfall, by that rain of fine sand and silt, right? So now you're thinking, you look at those places and you go, every flat place or low slope place is going to have a carapace of fine grained material that could be moved away. Here's the tourist industry on West Maui. Sugarcane is gone, tourism is here, and tourists don't like to swim in brown water. I don't either. And so more frequently now, folks are starting to notice there's a lot of brown water out there. And the questions are beginning to be asked. Like, hey, do you want to invest in a condo where you've got to go brown water swimming? What's going to happen to the reef? What happens to the fish? Right? So again, people want to know this. Where is it coming from? How fast is it coming? What can we do? Here's an image. Many of you have probably been. Honolulu Bay is one of the more popular attractions. Beautiful big coral heads on both sides here, and then the Valley of Honolulu here, headed up towards the peak in West Maui. These are multi-million-dollar estates, and if Maui Land and Pine eventually develops the rest of the mountain here, you will see this kind of multi-million-dollar estates scattered across much of this landscape. They're not going to do that, on the other hand, if it continues to look like this. This is an image of the same bay on a rainy day, and there's all this fine sediment pouring out of Honolulu, covering the coral, potentially threatening its survival, almost certainly threatening its survival. Again, nobody wants to swim in brown water. So the conventional notion was that all these exposed fields must be the source of the sediment, because you can see the red soil, right? So far we've been pretty good with that. Every time some red soil pops up, I go, look at that, see, it's a problem, right? And so you imagine, well, this might be the source here too. It turns out that in fact it is not the source for the plume you just saw. And here's why. This is an image of this field taken just after, the day after this rainstorm came and did this. And the only feature that shows you there's been flow in this field is this rill here, made by flowing water, but made by flowing water a long time ago, because what the rainstorm that happened the day before did is cave in the sides and not dig it any deeper. So that actually filled this in. There's no evidence for overland flow. In other words, the rain is so light it's seeping into the ground and not transporting sediment, and yet there's a big plume. So what's going on? So we made some measurements. This is an infiltrometer. It's used to tell you how fast the water infiltrates, moves into the subsurface. And then we have a number we call saturated hydraulic conductivity, which is a very fancy word for that number of how fast the water goes in. And that number is expressed in millimeters per hour in this table here, starting at 90, 80, 70, 60, 60, 50, 50, 50, 30, 30, 26, 12. So this tells you, we went and made these measurements across these fields. This tells you that you'd have to rain harder than these numbers in order to get erosion, right? Because otherwise the water just seeps into the ground. So how hard did it rain? Here's an image of West Maui. All these red places are places where there were plumes. This is a rainfall graph. I'm going to skip over for a second and move to this one. This is time on this axis, and this is rainfall intensity, how hard it rains. We said you had to be substantially above 25 in order to activate most of those fields. And in fact, what we find is the storm that happened is almost all under 10. So there's no evidence that the fields produced overland flow and erosion from that event, and the rainfall rates are too low to have done it. That's a pretty good correspondence. And yet there's a lot of plumes out there. Where are they coming from? If you wander to the edge of those agricultural fields, you will see this. This is a bunch of plastic drip pipe used for irrigation. In this case, it's a 60s or 70s era. And you can see that it's in a pile of soil that lies over the original old soil. We can tell this is old soil because it's got these vertical fractures in it that tell us it's been there a while. So here's a pile of sediment. And so if you walk a little further, you see that that pile of sediment cascades down the side of the slope into the valley bottom. And so wherever we looked, what we saw was that at the margins of those fields, fine sediment, that airfall, had been bulldozed and then pushed over. As they're shaping the fields, they need to shape the drainage. They need to shape it so that the water goes where they want it to go. And some of that soil isn't needed. So what happens? What do you do with it? Over the side, right? Now, let's say you walk down the slope to the bottom of the valley. What do you see? Red stuff. There it is. It's now sitting in the bottom of that valley. But now, all you've got to do is push a little water into the system, and that sediment is directly out on the reef. So what happened in West Maui, different from what happened in Molokai, is that agriculture took that airfall and pushed it right into the streams. And those streams, whenever they get up and flow, now move that sediment right out via bank erosion right out to the near shore. And they can flow at very low rainfalls. The numbers here show you the amount of the stream network length. So we actually went out and GPSed in where all the banks were. And it turns out that if you took the whole bank length on both sides, 40 to 55% of the total length has these kind of fine-grained sediment banks on it. And what that means is that every time it rains there, bank erosion will take fine sediment right out to that bay. It also means that if they were to develop the rest of these low slopes here and put homes and other things with asphalt and concrete, that the water that rushes off that is going to run into these channels, increase the discharge, and cause even more erosion. Consequently, if they're going to move forward, and I think they're aware of this now, they're going to have to make sure that all of that development drains internally as opposed to draining into the creeks, or they're going to make their blue water even browner. Okay, here's an image of what we were there on a day when we actually saw some erosion. So here's a rushing stream. This is Honolulu, actually. Decent rainfall. This is a little nail. That's one of those erosion pins. And it used to be flush, and now it's been eroded. And that one's still flush. This one's eroded, and I think there's another one up there that's eroded as well. So over the course of one day, we were seeing several millimeters of erosion off those banks, which means that probably those guys, the bank erosion rates there are about equivalent to the Molokai ones, which are 10 millimeters per year. That's a lot. So that's the story in West Maui. So we've gone through goats. The goat solution was get rid of the goats. And as soon as the community had the evidence they needed, they acted. And that system is coming back slowly. In West Maui, it's a more difficult problem. Agriculture has given them a legacy that now they have to deal with. Let's move on to the third one. The third one is fire. Fire influences landscapes by taking away all the vegetation. We all know that. The other thing it does, which is very interesting and still somewhat puzzling to us, is it also changes the rate at which water moves into the ground. And it does that in one of three ways, and maybe more, but at least one of three ways. When you burn all that vegetation and turn it into ash, that ash can clog the sponge, if you like, of the soil, and so it's harder for water to get in. That's one proposal. Another proposal is when you burn that vegetation, and you probably heard this, some of the vegetation goes into vapor as oils, and those oils redeposit and clog the pores again. That's two. And then the third option is that as you burn that soil, you make it really dry. And now to get water back in, that water's got to overcome the vapor pressure of the air sitting in the soil void. So all three are proposed mechanisms for what you've heard of as hydrophobicity, which means it's harder to get water into the ground, which means rainfalls that used to soak into the ground no longer soak into the ground, but now run off. Here's a graph that shows that. So here's a graph from Molokai that shows KSAT now is simply that number that tells you how fast the water gets into the ground when it's burned. And here's how fast it gets in for the same soil when it's unburned. Here's the 1-to-1 line. And let me interpret this for you. Essentially what I'm saying is you burn Hawaiian soils and you decrease the rate at which water goes into the ground by 2 to 4 times. 2 to 4 times. So now that means that rainfalls that used to soak into the ground are running off. Okay? So there's the background, or a very short backgrounder on what fire does. Now I'm going to take you to the last site, which is the Big Island of Hawaii. We're going to go to a place which is a recent purchase by the Department of Defense. The Department of Defense runs the Pauakalua training area, which I haven't shown here, but it's essentially this whole part of the island. 24th Infantry Division, 3rd Marines train there. They shoot their 105s and 155s to maximum extent. It's a pretty popular training base. The Army bought this patch from Parker Ranch, which used to use it as grazing, thinking that they could essentially run their strikers and run mobile there and do maneuvers. And they asked us to come in and survey it, give us high quality, high resolution data, and examine the geology so that they could get a base data set to figure out how to best use it. And in the course of doing that, we did a bunch of work, including an environmental sensor perimeter that tells us the amount of dust and water and soil moisture that move in and out of this place. But we also spent a lot of time walking around. When you walk around on that landscape to the north in the Hamakua area, you see deep soils, and in this case, this soil is that airfall. And you see a gentle landscape, but then you also see something else. Here's an image of that high-resolution LiDAR. It's a hillshade. And you can see this valley network in purple here. These are all gullies that have cut into that gentle, smooth surface, and they've cut all the way down to the underlying lava flows. And in this case, they're about 1 meter to 2 meters, 3 to 6 or 8 feet deep. And by doing so, they've exposed this section of sediments. So this is what it looks like when you're in one of those gullies. They can be pretty deep. And interestingly enough, there's a lot of stratigraphy in there, much more than one would expect, because I was always taught, again, as I said earlier, that Hawaiian islands don't have a lot of explosive stuff. But in fact, parts of them do. So here's an image of a cross-section. Geologists love these sort of things, so I spent a couple hours digging away. At the top is a lava flow. Right underneath the edge of that lava flow is a burned piece of vegetation, which we can date via radiocarbon. Turns out it's, what do I have here, about 42,000 years old. And then underneath that is this airfall section. It's weathered, and essentially all this airfall fell around 42,000 years ago, and then the lava flow came and buried it. So if we repeat this dating around the area I just showed you, what we find is that the lava flows sort of the lava flows and the airfall live between about 37,000 and 43,000 years ago. So what? This landscape has been sitting there accumulating soils slowly for 37 to 45,000 years. And yet we have this big gully system running through it. Something's not right. So then we started looking around, here's an image. The airfall is at the base here. It's this yellower stuff. It's a little bit difficult to tell. And then on top of it are aeolian deposits, sand and silt blown by wind now. So this is essentially like you took the airfall from the volcano and then just remobilized it and blew it around. And what we can see is that there's a thick section, it's 0.7, 0.8 meters, but then there's this curious dark brown layer here. And in that dark brown layer is a large burned branch, and that burned branch is around 1200 AD. So sometime 1200 years ago, there was a big fire, and then there was roughly 250 millimeters of aeolian deposition. Okay, that's interesting. We didn't see that in the underlying. For 38,000 years, this place has not been doing much. It turns out that, again, what fire does is reduce infiltration capacity, reduce the ability of water to go in. So here is, on the top, our measurements of what water should do if that place is not burned. So these are measurements we made in that area. And they range from about, let's see, I think that's 20 millimeters an hour all the way up to like 100. So in essence, they say, hey, you've got to rain harder than this in order to create erosion. But if you burn that place, look at what happens to those this distribution. It moves to the left, and all of a sudden, you've just got a rain 10, and then all of a sudden, you've just got a rain 5 or 7 millimeters per hour. So the likelihood is that by burning this place, all of a sudden, you've reduced its ability to soak water up, and you've increased its ability to channel water and create erosion. Now we started looking around and we started finding lots of very strange deposits. So here's that old airfall section, the yellows and the reds and browns, and then this little white layer. The white layer is an ash from a big fire. And on top of that ash is this section here. And if we look more closely at that section, we see a number of dark brown layers. A little hard to see in this image, but you see one there, you see one there, you see one there, you see one there. And if, in fact, if you were sitting there with me, you'd start seeing them all over the place. There's about 27 of them in this little section. And then we see imbricated gravels. Imbricated meaning they're arranged just like you'd stack books. And what this tells us is that the airfall ends about here, and this section to the top here are deposits put there by flowing water, not by air. And within those flowing water deposits are a series of burn layers representing fires. And when we started dating them, we found that they were 1299 AD all the way up to 1500, 1400 is a bit of a reversal here. And you'll see from successive ones that we can get almost up to 1800 AD. So here's another section, similar. See all these dark brown layers, those are burn layers, and then we've got alluvial material carried by water in between. And again, look at the dates, 1770, 1490, things like this. Over in this section, here's the airfall at the base. We have a very large branch, which is about 133 AD, a bit earlier than the others. Another big branch is 420. And then we get into our finer samples that are 1300s and 1400s, burn layers all throughout here. So what we found was that, in fact, this place had been fired, and all those fires seemed to happen, for the most part, between 1200 and around 1800 AD. Lots of fire layers. We then went out into the back into the big gully, and at the base of the gully, inset within it, are deposits that tell us more recent events. And in those, we can see that we have a little shell here that we can radiocarbon date about 1830. So what that means is, let's see if I got my picture. Let me go back to this picture. What that means is there was no gully here, and instead, somewhere upslope, there were fires, and sediment was sort of pouring down and depositing here up until around 1800 to 1830. And then, boom, all of a sudden, we cut a huge gully all the way down and deposited that sediment I just showed you. Now, let's look at all those radiocarbon dates together. So here's a graph. It shows you calibrated age and AD on the base from 0 to essentially modern, and then count the number of samples. We have two distributions here. One is coincident with ancient Hawaii. That's the Hawaiian, that's Hawaiians upon first arrival all the way up to around 1810, which is when Kamehameha formed the first kingdom. And we've got tons of rates. We have a gap, and then we have these older carbon ages. The older ages are almost all associated with big pieces of trees. So one interpretation of this distribution then is that the Hawaiians got to this landscape. The first Hawaiians get here somewhere around 1000 to 1200 AD. Almost the first thing they do is burn it. The big trees that are old with old radiocarbon fall in. Those are those old distribution of dates. And then as soon as they've reset the vegetation to modern carbon, those are the 12, 13, 14, 15, 16, 17, 1800 dates. And about once every 25 years, they burn the place, right? Or something burns the place. And consequently, you've turned a landscape that used to be a smooth, ungullied landscape into a landscape where each of these red features here represents a big, meter to several meter deep gully. And the consequence for the Army, as a consequence of ancient Hawaiian burning, the Army cannot use this to maneuver their Stryker vehicles. They were, straight. You'd think they'd have known that when they flew over, but they didn't. So that's the story of fire. It's the story of changing the landscape. So let me take a few moments to summarize what you've just seen, and then we'll take some questions. We started off with the question of where we can use mapping to tell us where the airfalls are exposed on original flow slopes or been redeposited as legacy stream terraces. There's no other way to do this. There's a lot of folks out there who want to just take topography and Landsat imagery and basically say, this is an erosion model. But unless you get out there and figure out where the sediment sources are, you can't answer the question. So it fundamentally requires that you get your boots dirty. You can use those other assets, and they're really valuable. But without getting your boots dirty, you can't answer the question. We then ask, well, is this amount normal? And I think what I've shown you is that in Molokai, it's over 100 times the long-term rate. Probably more, but at least 100 times. And that the banks in West Maui are eroding at rates that are also around probably closing up on 10 millimeters per year. I showed you, some examples of early monitoring, but I'm pretty sure they'll get up to that number or close to it. Then we ask, well, how much is coming down and how often does it come? I showed you evidence that essentially every time you rain harder than 10 millimeters per hour, crudely half an inch in Molokai, you start that sediment rolling down as long as it's exposed. If you get rid of the goats and the vegetation comes back, not a problem. We showed you that you can use an estimate of lowering rates that are proportional to the amount of hours the rain is more intense than the rate at which the soil can transmit water, or saturated hydraulic conductivity. Turns out 35 millimeters per hour is about the right answer there for reasons that we can go into. We made the argument in Molokai that about 1% of the landscape contributes almost half the load. Same argument is probably true for West Maui. The banks aren't big. Think about that for a second. That means if you're going to spend money to mitigate that landscape, you don't have to look at the whole 13 square kilometer catchment. You just have to look at 1% of it. And if you can grab that 1%, you can do most of it. In fact, that's part of the strategy with the goat removal. I showed you about a 10% reduction in lowering rate or erosion rate as the native vegetation took over in about 3 to 5 years. That's a political timescale. It means you can go to a politician and say, if you do this thing, you will see a result within your election cycle. Not bad. Just saying. And then we then talked about the impact of fire. Native Hawaiians began burning shrublands in the late 1100s, very shortly after we think they arrived there. They did it roughly every 25 years. And they did it in part because, in my opinion, I don't know this by the way, but it's tough to get through shrubs, right? Our native Californians did the same thing. You want to clear out areas where you can navigate quickly. Grasslands are preferable for that. It's tough getting around a'ali'i, which is this shrub. So they converted shrublands and treelands to grasslands using fire, and as a consequence, at some point, the effects of fire tend to last a couple years. So 2 to 5 years after you fire a place, you'll still see those reduced infiltration rates, the rate at which water can get through the ground. At some point when they burned, somewhere between 1800 probably and 1830, a big storm came just after they burned, and boom, all those gullies flower. So a coincidence. So widespread valley incision. They changed this landscape fundamentally. So what? Last slide. The so what is, ever since Homo sapiens erupted out of Africa around 60,000 years ago, humans have changed the landscape. Now here they've done it with lasting effect, and I'm sure they've done it elsewhere. It's easier to see here. The human impact on landscapes is ancient, and it's strong. And the more closely we look, the more we find that. We're engaged in a more synoptic version of this with global change. We're forcing it. Our community in the survey and outside the survey will be asked to tell people where, when, and how much for sediment, for water, for other things as well, and mapping and monitoring, two of our great strengths as well as modeling, are the tools that we'll use to do that. This could not have been done, the work that you just saw, could not have been done without all the folks over there. Ed Misaki is the guy on the right here. He's the visionary leader from the Nature Conservancy. It was Ed's vision to get rid of the goats. We supplied him with the arsenal, the scientific arsenal. Carefully phrased. We had help from all the folks there, and our equipment never got vandalized. Why? Because the people there in that community cared about the problem. Numerous people in the USGS helped the science you saw happen. This is a picture of some of them. There's Matt Rosner, the tall guy on the left, Jim Jacoby, Kevin Schmidt, Mayanna Hanshaw, and Todd Erickson on the right. In addition, sort of the godfathers of this vision of Ridge to Reef are Gordon Tribble and Mike Field, and then Kayana Bishaw, Kurt Storlazzi, Ron Rickman, Kim Perkins, John Nimmo, Steve Anthony, and many, many others were with me on this journey, and the journey's not over yet. So thank you folks very much.
Thank you. I'm sure that many of you have questions, and we have a couple of microphones. One's in this aisle, one's in that aisle. I'll ask you to please get up and use the microphones so that people watching this online can also hear your question beside the rest of us in the room. If you're not able to get up and walk to one of the microphones, just wave at me and I'll bring you one. So we have a first question over here. Why don't you go ahead?
Okay. I had a question about the West Maui and the agriculture. So presumably that agricultural activity was a while ago, 50 to 100 years ago even, right?
West Maui has been under agriculture since the 19th century, since mid-19th century.
So when they did this kind of moving around the sediment and pushing it off to the riverbanks, that's not a new thing. So the brown water shouldn't be a new thing on
Exactly
Maui.
the question Leslie asked me earlier. If you go and talk to folks who lived there in the 50s, they will describe huge brown water events. Oh, we couldn't go out fishing. It was brown water for weeks. The brown water is not what's changed. What's changed is you suddenly have people arriving there who didn't come there for agriculture, who didn't come there for fishing. They came there for blue water. That's what's changed.
The sugar fields, they burn annually, don't they? What kind of effect does that have?
Well, it's tough to say because that land has basically been out of production for over a decade, and so I lack the ability to go over there and measure. But you saw the rates from Molokai, which were, let's see if I can recover them. 2 to 4 times decreases in infiltration rate, meaning you can lower your rainfalls by 2 to 4 times and get runoff. I would guess that was potentially an effect, but I will tell you the other thing about the fields is that they are intensively managed, which means they are disking them, which disrupts that hydrophobic layer. They're doing lots of maintenance on them. It's in their interest not to see that soil go anywhere they don't want it to. And so from talking to folks who worked in the fields from the 40s on, they described the biggest issue they have to deal with is road blowouts. And they're always dealing with those. But the fields, they're pretty careful that, with sugarcane, they're internally drained. So they try and create pods. And then with pineapple, they try and basically create a surface that sheds the water off. I think it's a good question, and I can't give you an authoritative answer, but the one thing I can tell you is that the folks who work there believe that they did their best to reduce the amount of stuff coming off those fields when they're bare soil sitting there.
I'm struck with the similarity of a lot of the landforms, concavities, convexities, and so on in Hawaii with other things, both in the Bay Area and in the East Bay Hills, and also other places in the world. And I'm curious about is there work being done, or how applicable is this to other places? Could you talk a little bit about the larger global aspects of this?
Sure. There are a couple of aspects here that are generalizable and a couple that probably aren't. As you probably have gathered by now, knowing where the sediment reservoir, where the sediment supply is in the landscape cannot be done by theory. It has to be done by going out. And so there are places where that sediment is still in the hill slopes like Molokai, and there are places where it has been moved by people and other processes down into the valleys. The Bay Area, the East Coast, I'll give you an example. In the East Coast, it is estimated that the vast majority of fine sediment in the rivers of the East Coast is there because of legacy sediment put in by colonial farming. And so you could argue, and some have, that the majority of the sediment issue in the East Coast is a legacy of our colonial ancestors. And there are people that came after them. So there are similarities and there are differences. Differences are that the materials of the East Coast are going to have different infiltration rates and different rainfall rates. So you can't use exactly the same calibrations, but you can use the same techniques, mapping, monitoring, and modeling, to arrive at an answer. I would propose that's a much more stable answer than taking a theoretical model and bashing it to fit a place where you don't really know where the sediment is. So I don't know if maybe elaborate on your answer. I don't know that I've answered it because it's a pretty broad question.
Well, let me make one specific point out of it then.
Yeah.
One of the biggest things that here in the Bay Area and in Northern California is the impact of the placer mining and gold rush techniques that have largely filled in the bay with sediment and so on. Could you speculate on your theme here specific with the Bay Area?
Sure, the imprint of humans on the natural environment. Most of the estimates I've seen are that the majority of that sediment moved through the system by the time Gilbert got here, one of our illustrious ancestors, started doing his work in the teens. So it is widely thought that the majority of the gold rush deposits that are filling up that people are complaining about. I can't get the steamer up to Knight's Landing anymore because it's filled in. It's thought that the majority of that slug of sediment moved through the system, by the time the teens and 20s were here, and that we've essentially, recovered. Although I will tell you that studies in Sacramento show that there are large deposits of that sediment, and we can tell its signature as a higher mercury concentration left, but they're not currently being accessed. So I fear I haven't answered your question, but it's the legacy, the imprint of humans on the landscape is so varied that it cannot be answered with a single description, I think.
Hi. Hi.
Hi.
You just mentioned previously that you need the fine-scale mapping of the sediment sources, and you pointed out the hot spots where most of the runoff occurs. That was a fairly detailed map. It looked like it was done with some sort of remote sensing and not just dirty boots. How do you actually get that fine-scale mapping?
Great point. So the scale of the mapping really depends on the question to be answered. That's true for most maps, geologic maps included. In this case, what we understood was we needed to map at the scale that we could capture those features. And so what I did is acquire high-resolution LiDAR, that's imagery collected with lasers that gives you essentially every square meter, you have an elevation that has about this much uncertainty in it. So pretty precise mapping. I then had good remote imagery. And then what I did is every place I could get my boots on that landscape easily, I walked that imagery. I walked that topography. And I created in my head a correlation between what I saw with my boots and what I saw with my eyes on the imagery. And so that's the technique that people like Ray and Jeff and others here use when they're taking, because you can't be everywhere, right? You can't put your boots everywhere, but you can put your boots somewhere. And if you're intelligent about where you put them, then you can use that imagery to project that out across the landscape. And so you're absolutely right. I didn't put my boots everywhere. In fact, we used remote sensing. Yeah, ground truth. Well put.
Oh, we have one more question, it looks like. Okay. I have two more questions.
So now that you've done it a couple of times, if I gave you something like the military place with the gullies and everything, how long would it take you? How many boot steps do you need to get a overview of the?
It sure is easier to do stuff the second time around. Probably about half the time. I think that's sort of that's why, although I'm more expensive now because I'm older, I'm also less expensive because I take less time to do it.
So years?
How many years? It didn't, the Molokai mapping could all have been done in about a month and a half had I been there continuously. It wouldn't have been as valuable because I wouldn't have the chance to have a dialectic, this sort of conversation with others and yourself. And so it was done in sort of 2-week field patches. And it was done in about 6 or 7 2-week field patches. And by doing that over the course of a couple of years, what I was able to do is essentially learn how to do it right. And so, if I were to go and map Molokai again, or a place like it, instead of 6 2-week field episodes, it'd probably be 4. I'm guessing, but it's about, you do gain efficiency, as people like Ray or Jeff will tell you.
There are areas in Hawaii which were used for agriculture for decades, maybe centuries, and then abandoned.
Mm-hmm.
And presumably after they were abandoned, they would start to go back to their natural, let's say, pre-settlement arrangement. Is that happening? And if it does happen, how long does it take?
Well, I mean, as you probably know, the big story in Hawaii is invasive species. And so when you leave something alone, it's usually something different that comes in to recolonize it. The Molokai was a little exceptional because, in essence, remember that sort of Pelekunu Valley and that sort of pristine environment I was showing you? That's upwind of the site we saw. So any of that seed bank essentially is going right into our field site. So we're very lucky in that sense. Molokai is lucky in that it has this native vegetation seed bed. It's just downwind of it. So that's seeding. Most places in Hawaii, they're concerned about invasives, anything from strawberry, guava to bufflegrass. And so former ag places are hotbeds of invasive species, some of which may actually do a pretty good job of shutting down erosion, and others, it's debated. And so one of the controversies that's going on right now is, let's say you want to turn your brown water to blue water again, and you think you've got something like vetiver grass, which is an invasive, but it's relatively controllable. Should you just throw that on there and say goodbye to endemics and native vegetation? Or should you take longer to try and get natives and endemics to come back? And no one really knows the answer to that. It's a priorities issue. Everybody knows that they want a landscape that's more like Hawaii before humans got there, but we also know there are costs to that, economic costs. So that's a debate. Watch that debate play out. I don't know what the answer would be.
One more quick one. Could you comment just a moment on the reduced tillage or zero tillage agricultural techniques? Are they using much of that in Hawaii, and how hopeful or how effective do you see that in the big picture?
I don't know a lot about that, and so I won't have a good answer for you. I will say this: agriculture in Hawaii now is largely done out of personal preference, not industrial. There's very few industrial concerns going. On Molokai, Monsanto, essentially, because you can do 3 crop rotations in that climate, runs a lot of their experiments there. But most of the agriculture being done in Hawaii is for farmers markets, and it's usually done in a way where folks are convinced that they're not creating a problem, because all their neighbors would be on their back if they were. So I can't answer your question. I don't know those techniques well enough to answer.
Okay, we have one more question, and then we'll call it a night.
Where you had those very deep gullies and so on, what's that land going, if you don't do anything, what's that land going to look like 10, 20, 30, 40 years from now? In other words, what sort of
where's it headed?
Natural repair might be done?
The gullies now act as their own runoff generators. So what you will see without any intervention is the gullies will very slowly expand, and the bigger they get, the faster they'll expand until they essentially eat up all of the sort of valley network they can eat up. They will not heal themselves.
Well, I'm delighted you had so many questions. Must have been a good, thought-provoking talk. So thank you very much, John. Thank you for joining us. And I'll say aloha until next month.
Very nice event.
No, I know.
Difficult.
It doesn't turn off easily. It's all right.
You mentioned Santa Cruz Mountain.